Hey, Rokia.
Hi, can you hear my voice?
Yes, I can hear you. Can you hear me?
Yeah.
I see. That's good. How are you doing today?
Good, how are you?
That's good. That's good. Okay. So for today's office hours, do you want to go over midterm two reactions and mechanisms? And then we can review your midterm one mistakes. When we review for the final. Like we don't have to worry about that now. Like that's definitely the drop one, but we don't have to worry about that now.
Yeah, I wanted to review like stuff for midterm too, because that's like coming up next week.
Right. Okay. Okay. Let's do that.
Thank you.
Do you have any questions or problems to get started with? Or if not, we could just go over reactions and mechanisms, and I could come up with practice problems for us to go through.
Yeah, that would be great.
Okay. Okay. Let me do that. Okay. So for midterm 2, it's all about chapter 21 and chapter 22. Chapter 21 is all about the amines. Chapter 22 is about the phenols, like the benzenes with the alcohols on them. So let me just pull this up so make sure that I teach Helix 118C midterm. June material. Okay. Okay. So let's get started with the reactions and mechanisms. So synthesis of amines. Let's talk about how to make amines. The first method that you learn is the alkylation method, which is a problem. It's not the best way, right? Because you're gonna have this halo alkane right here, let's say for example, and when you use ammonia in excess, right, that's going to act as a nucleophile, and when that acts as a nucleophile, this is going to be our electrophile right here, where we're going to attack this electrophilic carbon, kick off this good leaving good bromine, and we're gonna have this ammonium salt right here, right? Where this nitrogen here can be deprotonated because it has a proton for us to deprotonate and neutralize, right? Because it has a positive charge right now, and that's not favorable. So for us to neutralize it, we could use another NH3 base as a second equivalent to grab that hydrogen, and the bond between this hydrogen and nitrogen right there is going to go onto that nitrogen to give us this neutral amine right here. Now once we have this neutral amine can be the nucleophile for the next reaction when we bring in the second equivalent of this halocane right here. So we're going to do SN2 again one more time, where this nitrogen attacks that carbon, kicks out the bromine, and we now get this amine where it has two R groups, and that nitrogen has a positive charge now because it has four bonds. But notice how this nitrogen here still has two protons, and because it still has protons, we can still deprotonate it and make it neutral, right? So we're gonna keep going with this reaction until the amine no longer has a proton for us to deprotonate, right? So we're gonna over-alkylate this amine until we can no longer deprotonate and neutralize this nitrogen right here. That's why this is a problem, because we do not want that in lab, let's say, for example, right? So that could come up as a conceptual question, or it might even be a predicted product question where you would have to go all the way through this over-alkylation where the nitrogen is positively charged and you cannot deprotonate it. Right. Okay. Any questions on that, Rukia?
No.
Okay, that's good. Now the next one is going to be synthesis of primary amines, and keep this in mind because I've seen on his exams where he asks like which reactions can create a primary amine only, which reactions can create any kind of amine, like a primary amine, secondary amine, or a tertiary amine, right? So these reactions here are going to create primary amines where a primary amine is going to have one R group, just like that. A secondary amine is going to have 2 R groups like that. A tertiary amine is going to have 3 R groups like that. A quaternary ammonium salt is going to have 4 R groups like this, where this nitrogen is going to be positively charged because it has 4 bonds, right? But you can also have an ammonia where there's no R groups, 0 R groups, and that's referred to as ammonia, right? NH3. Okay, so let's look at the first one, which is reduction, and we could reduce nitro group, nitrile, and azide. So back in 118B, which is this right here, do you remember this structure, Rukia? Like, did you have 118B with helix?
Yeah, I
Uh,
did. Yeah, I remember it.
yeah, that's good. Do you remember the name of it? It's one of the common names that you have to memorize in that midterm.
I think I'm blanking on it, but I
Uh-huh.
remember like the structure.
Right, right. What about this? Do you remember if it's an EDG or EWG? Ortho para director or meta director?
Oh, that was a meta director, I think.
Yes. This right here is a meta director, EWG. Is there a way where we can convert this meta director or EWG into an ortho para director or EDG? Like this group here into an EDG?
Yeah,
Uh-huh.
I think it was like when we bring the S double bond O, like there's a bunch of double bonds to it, and then we could like make it an ortho
Mm.
para or like a meta.
Uh-huh.
Oh, I
So
think it was.
you're thinking of the sulfonation reaction with the SO3H H2SO4, which like serves as a protecting group for the para position. But what this can do is this can turn into NH2 right here, aniline. Right, this is nitrobenzene here, which can turn into aniline by reduction. And we could use reducing agents like H2PDC. Does that sound familiar? H2PDC.
Yeah,
Or clementine reduction reagents like zinc, mercury, and HCl. Right?
yeah, that.
Yeah. So the reason why this reaction is coming back is because we are creating an amine here, and this is what this chapter is all about. The amines right there, like that.
Mm-hmm.
Right. Okay. Now this is gonna go back to I think 118A. You learned about this or no? Maybe no. I don't think you have learned about this. Nitrile reduction. Where let's say you have this CN nitrile right here, which when you see CN, right, know that there's a triple bond between the carbon and nitrogen. So there's gonna be a triple bond between this carbon and nitrogen right there, and you could reduce this nitrile with a strong reducing agent like lithium aluminum hydride, right? Or you could use H2 with some kind of metal catalyst, right? And this metal catalyst can be in the form of rainy nickel or plutonium O2. So be careful here because how many carbons do we have in the original reactant? Like in this reactant here, how many carbons do we have?
4.
4 carbons, right? Because a lot of students forget that the carbon of the nitrile is included as well. So when there's 4 carbons like that, make sure when you reduce it, this maintains as 4 carbons, where this is carbon 1, carbon 2, carbon 3, carbon 4, right? The starred carbon here, the nitrile carbon, carbon 1, is that carbon right there.
Mm-hmm.
Uh-huh. Okay, so the next one is going to be azide reduction, right? And this one here is going to be N3. So let's say we have this N3 right here. To reduce it, we could use lithium aluminum hydride with some acid workup afterwards, like H2O or H2O plus, or you could use H2PDC, right? And that's gonna reduce this azide N3 into NH2. And we had 1, 2, 3 carbons to begin with, so we're gonna end with 1, 2, 3 carbons there. The N3 here becomes NH2 from this reducing agent right there. Okay.
Mm-hmm.
Now let me give you a 2-step synthesis problem based on what we just did right here, and see what you get. Okay, let's say we have this structure, And I want you to synthesize this product right here, like that. Okay. Tell me your thought process, what you're thinking, and how you would approach it. Like you could go two ways. You could go forward or you could go backward, retrosynthesis or forward synthesis.
Okay.
Uh-huh.
So we would add like NH3 to kick off the BR. So, and then just like how we did in the beginning, we would have like,
So when we add NH3 right here, right? Assume excess
mm-hmm,
amount of this and assume excess amount of the haloalkane. This right
mm-hmm,
here is the very first thing we went over, which is overalkylation of the amine, right? So if you have any haloalkane, like the one we just had that I showed you, and you add
mm-hmm,
NH3 right there, it will not stop at this
that one.
form, right? Because we
Mm-hmm,
have excess amount of this. It's gonna keep going all the way until we get the positively charged nitrogen that can no longer be deprotonated, right?
mm-hmm.
So let me give you a hint here. How many carbons do you see here versus here? Like, do they have the same amount of carbons or do they have different amount of carbons from
They
this
have
structure?
different amount of carbons.
Right, different amount of carbons, where we see this one here has one extra carbon. So what method do you think that we have to use here? Do we want to use NaCN as the first step, or do we want to use NaN3 as the first step to get that extra carbon that we want?
Um, I think we would use the C3. Oh no, CN, sorry,
Yep.
to get an extra carbon.
Right. We want to use NaCN, where the CN minus, right, that is going to attack this carbon, kick out the bromine, and that's going to give us that extra carbon that we see in the product, right? So this is going to be like that, where we substituted this bromine with the CN. That's a simple like SN2 reaction from 118A. But we see that we added an extra carbon as a result of that reaction, and we want that extra carbon because we see in the product there's an extra carbon right here, where
Mm-hmm.
to finally go from here to here, what reagent would we use to convert the nitrile into the amine, primary amine? There's two possible ones that you could use.
The LiAlH4.
Yep, you could use LiAlH4 and then acid workup afterwards. And that's it for the synthesis, right? We could not use NaN3 because if we were to use NaN3, we would not add that extra carbon and we would get something else, right? When we reduce it with LiAlH4, right? If we use NaN3, we're gonna get this, and then when we use LiAlH4 with acid workup, we're gonna get this product here, where the N3 gets reduced into an NH2, which is not the same thing as this desired product that I gave you because it has one less carbon, right? So it depends on the synthesis problem. If your product has like the same amount of carbons, then you want to go through this route, the NaN3 route. But if you see in the product that you have one extra carbon, you want to go through this route where you add the NaCNN.
Okay.
Right. Okay. Now, the next one is going to be about Gabriel synthesis. So this one here is going to be a very distinguishable reaction, right? Because there's a very distinguishable reactant that you can use with this reaction here. So Gabriel synthesis, and this is going to create a primary amine. So you're going to have something called a phthalimide, which looks like this. And we see that this hydrogen here is acidic because it's attached to the nitrogen. So when we put any kind of base, right, like NaOH or NaNH2, the common one that's used here for Gabriel synthesis is going to be carbonate ion. So it's going to be K2CO3. This base here is going to grab the hydrogen and the bond between this hydrogen being grabbed and nitrogen right there is gonna go off and go onto the nitrogen, right? The 2 electrons in that bond are gonna go to the nitrogen, giving that nitrogen a negative charge. Right. Now, we see that this negatively charged nitrogen is now nucleophilic, where we could put any kind of primary haloalkane in to attack and do SN2 reaction, right? So let's keep it simple for now and put this simple haloalkane right there, where this negative charged nucleophile nitrogen is going to attack this electrophilic carbon and kick out the good leaving group bromine for SN2 reaction, right? And that's going to give us this right here. Okay. Now, to keep track of everything, this is what I recommend doing. Keep track of this carbon right here, which I'm going to color code in blue. That's this blue carbon right here. This is the neo bond that we made between this nitrogen atom and this carbon right here. Right? And we see that this blue color-coded carbon here is attached to a methyl group, which is this methyl group right here. And the bromine got kicked out. Now, this is going to be a Mitten-1 reaction here. If I put acid, like H2SO4, water, and heat, do you remember what kind of reaction this would do based on this reactant here? Like, what functional group do you see present in this reactant here?
The N and the methyl group, that's the new one that we made, and then the double bond O.
My iPad is being frozen right now for some reason. Hold on. There we go. Yep. Yep. So we see the N and the carbon double bond oxygen. So this is a carboxylic acid derivative, specifically an amide, right? And any carboxylic acid derivative, when you put that through acid, water, and heat, will do hydrolysis, right? It will always go back to the parent functional group, carboxylic acid. So to predict the product quickly here, do you know how we would do that? Or yeah, how would we approach that? Like to predict the product quickly here?
Would we like go back to like H and then H2SO4, the double bond O, and then it would attack the H. It would take a hydrogen from it, so it would become positive. And then
the carbonyl oxygen will grab the H from the H2SO4 and becomes H and becomes positively charged, right? Yeah.
And then the H2O will attack from the bottom, and then that will go up.
Correct. Yeah, so that's the correct mechanism. Nice. But if this was a predicted product problem, right? I don't recommend doing the whole mechanism. I recommend just getting straight to the product because that's gonna give you the points, not the mechanism. So here's what I would do. Find the carbonyl carbon, which is this carbon right here, and make a cut between that carbonyl carbon and the nitrogen right there. Right? We have another carbonyl carbon here. And this is the LG. Think of this as the leaving group, right? The leaving group is the amine. And make a cut right there. This amine right here that I am circling right now is going to become the primary amine. Right? So this whole structure here comes from this right here, the LG, the leaving group. Right? Now, the carbonyls here will become carboxylic acids, right? Because we're doing hydrolysis. We're resetting back to the parent functional group, which becomes this right here. And these are our dioic acid here, our 2 carboxylic acids that we have from that hydrolysis reaction, right? We had a cyclic amide that got hydrolyzed down into the carboxylic acid, and the side products here, or the main product, because we're in this amine chapter, is this amine right here, which comes from this right here, like that.
Okay.
Right? Okay, that's good. So now the next one here is going to be Hofmann Rearrangement, which is also a midterm 1 reaction, where I'm going to give you, let's say, this reactant right here, and I'm going to give you this reagent, and imagine this is a predicted product problem. NaOH, Br2, water. Do you remember the name of this reaction and what this would do to this primary amide right here?
So, it would add a, actually,
I think you're thinking of the HVZ reaction, right? The Helmholtz-Zielinski, when you add the bromine to the alpha carbon of the carboxylic
Yeah.
acid. Yeah, that's something else. It has very similar reagents, right? HVZ is gonna have a carboxylic acid, not an amide, right? So like because that's not a carboxylic acid, we know that this is not gonna be HVZ. But let's say we did have a carboxylic acid right here. The reagents that you would see for this is gonna be PBr3 trace,
Mm-hmm.
Br2, and that's gonna add bromine to the alpha carbon, right? Which is this carbon right here, because if this is the carbonyl carbon, the first carbon away from the carbonyl carbon is the alpha carbon, which is this carbon here, and we're just gonna add a bromine there. So we're alpha brominating the carboxylic acid from HVZ. Midterm one. Did that show up in the midterm one
Yeah,
test? It did?
kind of.
Okay. Okay. That's good. Yep. I still need to check
So
it.
would we just be like taking out the NH2 and adding OH to this then?
Oh, you're thinking of hydrolysis, right? If it was just NaOH and no Br2 and with H2O,
Mm-hmm.
it would be hydrolysis, right? So let's do that. But because we're in basic conditions here, we do not stay in the carboxylic acid form, right? Because this is acidic. A, a base like OH minus here is gonna come in and deproteinate that acid, right? So I'm gonna put this as the intermediate because it does not stay there. That's not the final product in basic conditions. It would become deprotonated to become this carboxylate here in basic conditions. And then if you want to do acid workup like H3O plus, then that will become the carboxylic acid. It will go back to the carboxylic acid. But for helix class, even if he doesn't put like, let's say second step acid workup, right? If you put this as the answer, you still get full credit because he assumes that there's an acid workup step,
Mm-hmm.
right? Okay. But with the primary amide, when you see NaOH water with Br2, that is Hofmann rearrangement. Hofmann rearrangement, which will convert this entire amide here into the primary amine, like this, right? And what do you notice about the carbon atoms of the molecule compared to the reactant molecule and the product molecule? What do you notice about the carbon count?
It like it got reduced.
Yep. There's one less carbon, so minus one carbon. This carbon here is not there anymore. Right, so the carbonyl is gone. This entire amide got converted into this amine right there. So that's the most important feature about this for synthesis. Right, so if you see one less carbon, you could think of this reaction here. Like you want to get to this primary amide somehow, and then you could get rid of one carbon by doing Hofmann rearrangement using these reagents here, which will get to this amine.
Okay.
Okay. Okay. So the next one here is gonna be reduction of amides. So let me actually get another page here because I might need more space for this one. Okay. So let's say I have a basic amide to start off with, like this. I could use lithium aluminum hydride with an acid workup. To completely get rid of the carbonyl of the amide. So this is also midterm 1 reaction, reduction of amide, where we just completely get rid of that carbon double bond oxygen to get the final answer right here. Now let me give you a synthesis problem that is all midterm 1 material, right? So let's say we have this and H2 and synthesis. We want to get into something like this, like that, with a hydrogen up there. Okay, so we see that we came from a primary amine into a secondary amine. I'll give you a hint. We could go backwards here, right? Where we see that this is the new group that we're adding. let's say that this carbon here had a carbonyl, right? A carbon double bond oxygen, like that. What reaction would convert this intermediate into this product here?
It would convert it into that.
Yeah. What agent? What reagent would convert this molecule into this molecule here?
It would be the ALH4 and H plus workup.
Yep. Li ALH4 and H plus workup would reduce that amide into the amine. Now there is one reaction that we could do to convert this amine into this amide right here, but it's kind of organized very weirdly because you're used to seeing this amine as the reagent and whatever this is going to be as the reactant, right? But imagine this as this part of the structure right here. Where do you think this part came from? Like what can we do to
that was
get
added
this?
on?
Yep.
We could use the LDA, and then we can have. Actually, wait.
LDA would deprotonate the amine to get the N minus, and then the N minus. I think you're thinking of adding this to like some kind of haloalkane to do SN2, right? But we have a carbonyl here, which is gonna be problematic. If this was like just an R group, then that would be valid, right? Like we could use LDA to get the minus charge here, and then we could add this haloalkane, kick that bromine out to get to this point here if there was no carbonyl. But because there's a carbonyl here, this is an amide, and that's a carboxylic acid derivative. And do you remember what's the most reactive carboxylic acid derivative, like the most reactive one?
The most reactive as in like out of all the groups?
Yep, out of all the groups. Like amide, ester, carboxylic acid.
It was carboxylic acid, I think.
Carboxylic acid is in the middle. It's in between. It's neutral.
Oh,
right. There's two functional groups that are more reactive than that, and right, it's the.
I think I have it. I just don't have it like memorized off top of my head. But
it's
I know amide is the least.
Yeah. Amide is the least, correct.
And then.
Do you have a guess? It's okay if you get it wrong. Like any guess? Any guesses?
I think. I can't find my note card because I had it on there, all of them.
Yeah. Did you use my note card, or did you make your own note card?
I made my own because like that's how I practice more.
And you find like it helps you study while you make it, right? Like as you're writing it, like you like understand it and you know where it is better.
Yeah.
That's good. That's good. Yeah. So the two most reactive derivatives that are more reactive, acyl halide.
Yeah.
And
anhydride.
Anhydride, right. So acyl halide, since it's the most reactive one, it could do all of the reactions. It could convert to any of the lower reactive derivatives in one step, right? It could get into the anhydride in one step. It could get to the carboxylic acid in one step. It could get to the ester in one step, and it could get to the amide in one step. So we know that this part here came from this amine, but this part right here, I'm gonna make a dashed line right here to show that this part of the molecule right here is gonna come from the acyl chloride like that, where this chlorine here is the leaving group, and we're basically substituting this leaving group with this nucleophile here minus one hydrogen to get this point right here. Does that make sense so far? Right, but you're usually seeing this as the reactant, right? And you usually see that as the reagent. This is kind of reversed now, so it could get tricky like that, right? But you're gonna need some kind of base like pyridine or T with this to make an amide, right? Okay. And the reason why is because in the mechanism, the intermediate would be positively charged, and we need some like kind of strong base to deprotonate that positive charge, which is why we need pyridine or T to deprotonate it. Cl minus, when it gets kicked out, it's a weak base because it's so stable, right? The negative charge on this chlorine is very stable since chlorine is very electronegative. So that's why we need pyridine or T to do that.
Okay.
Okay, so the next thing here is going to be very important, reductive amination. So reductive amination is going to have a review from 118B. We're going to have an aldehyde or a ketone reacting with an amine in acidic conditions. So let me put that acidic conditions in, which could be in a pH of like around 4, which is what Helix uses, to get the amine or iminium ion. But we're going to focus on the iminium ion for this reaction, reductive amination. So let's get started with that. So let's start with off simple with this aldehyde right here. And let's say I react it with this primary amine at a pH of around 4. You don't need to work the mechanism for this because that's 118B and you've already like tested on that. But for 118C, this is what you need to know about it. This carbonyl carbon right here is going to become an iminium carbon, right? Instead of a carbon double bond oxygen, we're gonna have a carbon double bond nitrogen, where the nitrogen here is the nitrogen of the amine, like that. And this nitrogen here is attached to an ethyl group, which is this ethyl group right here, and 2 hydrogens, right? But we can only add 1 hydrogen to conserve the octet role, right? 1, 2, 3, 4 bonds. And what charge would nitrogen have with 4 bonds?
Plus.
Yeah, plus charge. And this right here is what we call our iminium ion, right? And then from this iminium ion, this is the second step of reductive amination. We use the reducing agent NaBH3CN, which is a reducing agent that would reduce the iminium ion into the amine, right? It's basically converting the carbon double bond carbon double bond nitrogen into a carbon single bond nitrogen, and it makes the nitrogen neutral, like that. Okay, and we see that this iminium carbon here had 0 hydrogens, but now it has 1 hydrogen, like that, because this 1 hydrogen here that was invisible came from the reducing agent NaBH3CN, like that. Okay, so that's reductive amination. Let me give you a practice problem with that is a little bit more difficult here. And then you can send it to me on like school or show me your screen or email it to me. Let me give you this problem here, like this. This, and let me give you this amine. First step, at a pH of around 4. Second step, NaBH3CN. Okay, or you could describe it to me, like what the product would look like. You could describe to me what the first product would look like, and then after that, what it would look like after the second reaction.
So would it be basically just like the same? Okay, the N with the ring on it would come on where the O is, and then one of the bonds will like go in, will leave, and then would that just be it? So there's just like one bond.
Did you get this as the first
Yeah. And
step?
then the second step would be like that the double bond would come to a one bond.
Yep, one bond and the positive charge disappears after that, and this is the final answer. Correct. That is reductive amination, and reductive amination is very powerful because we can create a primary, secondary, tertiary amine. In this case, we created a tertiary amine without overalkylation, right? Like without having the nitrogen have a positive charge. So this is a very powerful tool. Okay, nice. The next one is gonna be Hofmann elimination. Okay. So for this one here, 118A Hofmann E2 is gonna come back versus Zaitsev E2. Let's start off with a simple example with this primary amine, right? This looks secondary because this is a secondary carbon, but this right here is considered primary amine because this entire group here is an R group. And this nitrogen is only attached to one R group, which is this R group right here. So this is a primary amine with 2 hydrogens. The 2 reagents that you're going to see for this reaction, Hofmann elimination, are these right here. First step is going to be excess CH3I in basic conditions, K2CO3, water. And then the second reaction you're going to see is Ag2O, water, and heat. So the first reaction here is what we went over at the very beginning of the session. What would excess CH3I do with this amine right here?
So it would take all like the H's and then it would add a CH3.
Correct. It would take all the H's and it would add CH3s. How many times? Like until it's neutral or until it's positively charged?
I think it was until it was positively charged.
Right, until it's positively charged. We cannot do it until it's neutral because if it's neutral like this with 3 bonds and a pair of electrons, this pair of electrons here is going to attack another excess amount of CH3I, which is why we can add another methyl group here. And when we do, this nitrogen has 4 bonds, which is positively charged. And we can't do anything after that, right? We cannot deprotonate it because there's no proton. We can't add another methyl group because there's no more pairs of electrons for us to use to attack another methyl group. And we already have the octet row. Okay? Now, once we have this, think of this group right here, the nitrogen with the lot of methyl groups, as the good leaving group. So think of it like a bromine, chlorine, or iodine. Now, the Ag2O here, the base, comes in as a bulky base. Think of it as hydroxide ion, but it's bulky, right? Like LDA or turbotoxide. So would you grab HA or HB to get the Hofmann alkene? The less substituted alkene.
Then I would grab the HB.
HB, correct, because HB is less substituted than HA. So we grab HB here. The bond between HB and carbon goes over to make a bond right here, right? Which creates that double bond. And we kick off this leaving group as a result to give us this final product here, which is that less substituted E2 Hofmann alkene and this trimethylamine, which is the key to stop this reaction right there. Okay, so that's Hofmann elimination, but it can get tricky because when you like do leave-ins practice problems or the AATC ones, you can get rings and you could have it go multiple times, which I'm going to show you here as an example. So let's say we have something like this. All right, let's say this is hydrogen, and we have that, and then we are going to react it with the Hofmann elimination reagents, where the first step is excess CH3I, K2CO3, water. Second step is Ag2O, water and heat. Okay, describe to me how you would approach this problem.
Right. So like how we did in the last one where we had the excess CH3I and then we kept adding methyl groups. So it would be CH3 to the NH until it's plus. And
Mm-hmm.
then for the Ag2, for that one, it would kick off like we did last time, the N, and then it would add to the less substituted carbon.
Right, correct. And I'm gonna give you a trick here to find out the correct hydrogen to take, right? Especially when you have like many multiple options to do so. In this case, it was simple
Mm-hmm.
because this is the Lg here. This is the alpha carbon because it's the first carbon away from the Lg.
Mm-hmm.
These are the beta carbons because they're the second carbon away from the Lg. And notice how here we're grabbing a beta hydrogen, right? So for Hofmann reaction, we're looking for the least substituted beta hydrogen, right? So looking at this case right here, these purple carbons right here, the one directly coming off of the nitrogen are the alpha carbons.
Mm-hmm.
The
So,
green carbons right here are the beta carbons.
oh,
Right, there was a sneaky one, right? You didn't see this one, right?
yeah, no,
Yeah. Did
because I
you
was thinking,
choose this one to grab and make an alkene here
yeah.
and kick it off? Yeah, that was the trick, right? This guy here is hiding from you. This guy is the least substituted one, right?
Mm-hmm.
Because there's 3 hydrogens right there, which are gonna get grabbed from the OH minus in the second step, make a double bond here, and kick out that leaving group like that, right? So be careful of that. Be careful of this guy here.
Okay.
Okay. Now that's gonna give us, oh shit, that bond is breaking now, broken. So we have that, and then we have a double bond right here. Nice. Okay, but we do not stop here. We know when to stop when we have this trimethylamine in the end product for helix, right? We do not have that yet. We have this, but notice how this nitrogen here has a pair of electrons. That pair of electrons can attack another CH3I to become over-methylated with a positive charge. And in this case, we only have one option, right? Where this is the alpha carbon, this is the beta carbon. Be careful, right? Because a lot of students try to take the hydrogen from the alpha carbon, but you can't do that because if you take that alpha hydrogen right there and you make a double bond right here, you can't kick anything out. Like there's nothing to kick out. Right? So you gotta grab the hydrogen from the beta carbon, right? Grab the beta hydrogen with the OH minus, make a double bond here between the alpha and beta carbon, and kick out that leaving group, right? This right here is the Lg, the leaving group, which will lead us to our final product. Like that. And because this is organic, I would include that as well in the answer. Okay.
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 Let's see.
Any questions on this before we move on to Mannich reaction, which is the biggest reaction of chapter 21?
No.
Okay, let's move on to Mannich reaction. Chapter 21's biggest reaction. So it's like an aldol reaction from 118B, but we use an iminium ion instead of an aldehyde or ketone. So to break it down easily, the nucleophile for Mannich reaction is going to be an enol. The electrophile of the Mannich reaction is an iminium ion. The product of the Mannich reaction, to make sure that you have everything, is going to be a beta amino carbonyl. And it'll make more sense when we go over an example. Okay. And there's going to be 3 reactants in acidic conditions for Mannich reaction. The enol will come from an enolizable carbonyl, right? That means that it has an alpha carbon, hydrogen. Alpha hydrogen. The iminium ion is gonna come from an amine plus some carbonyl, right? And that carbonyl typically is not enolizable. And a beta aminocarbonyl looks like this. So let's say we have a carbonyl right here. And this is the carbonyl carbon. This is the alpha carbon. This is the beta carbon. And at that beta carbon right there, we're going to have some kind of amine group, like let's say NH2 or NRH or NR2. Okay? Now, here's an example here. Let's say we have these three reactants. And we react it with acidic conditions with heat. And you can see alcohol there as well as the solvent and base. Okay? I'm not going to go over the mechanism here, but I will show you how to predict the product quickly and how to go backwards if you're given a Mannich product and you want to go backwards for synthesis. Okay? So now we have a ketone here, we have an aldehyde here, and we have an amine here. Do you remember back in 118B if the ketone or aldehyde was more reactive and why? It's okay if you don't remember. It's been a long time.
I think it was the ketone.
The ketone
Or was it?
here is not more reactive. It's the aldehyde, right? The aldehyde has a bigger positive charge on the carbonyl. The reason why is because this carbonyl carbon here, right, only has one R group donating electrons to it. The hydrogen here is not donating any electrons. Whereas the ketone, it has a smaller partial positive charge because it has two R groups donating electrons to the carbonyl, reducing the charge, reducing the positive charge, right? So the aldehyde is more reactive there, right? So that's why the aldehyde here is going to react with the amine to become the iminium ion, right? And here's how we could do the iminium ion. The carbonyl carbon of the aldehyde will become a carbon double bond nitrogen, right? Where the nitrogen is the nitrogen of the amine. And the nitrogen there is attached to a benzene ring and hydrogen. And that's positively charged. This is the iminium ion here. Does that make sense so far?
Yeah.
Right, okay. Now, this ketone here is going to be the enol, right? And for something to be an enol, like for a carbonyl to be an enol, it needs to have at least one alpha hydrogen. So if this is the alpha carbon, we see that that alpha carbon has three alpha hydrogens, but we only need one alpha hydrogen to make it into an enol. Like that, okay? Now, do you remember what was the nucleophile in this enol here? Like, what is the atom that attacks an electrophile in this enol molecule?
Would it be the oxygen?
It looks like the oxygen, right? Because it has pairs of electrons, but it's actually going to be something else, and it might help if I draw you out the resonance structure. Right? These are resonance structures of each other, where now look at the resonance structure. What's the nucleophile? What's the actual nucleophile?
It's the negative charged CH3.
Yes, that negative charge CH2. There's no more, like, this is a CH2 here because 2, 4, 6, 8. Wait. 2, yeah, 2, 4, 6, 8. 1, 2. Yeah, this is the CH2 because it can have CH3. If it has CH3, that's gonna big dog octet row. 1, 2, 3, 4, 5 times 2, 10 electrons. Yeah. So for the enol, the alpha carbon here is the nucleophile. The electrophile is gonna be this iminium carbon right here. Okay. Now, to predict the product quickly, this is what we're gonna do. That nucleophile is gonna attack the electrophile by having the carbonyl get reformed. The star attacks the dot pushes, the double bond pushes up onto the nitrogen, giving us this final product right here. This is the star. This is the new bond between the star and dot. The dot here is attached to nitrogen, hydrogen, benzene. and a methyl, right? This methyl of the dot is that methyl right there. And the hydrogen here of the oxygen gets deprotonated in the mechanism somewhere. But this is the final product of Mannich reaction, which is a beta amino carbonyl, right? Because at the beta carbon, we see an amino group relative to the carbonyl.
Okay.
Okay. So now that was one example. Let me show you an intramolecular reaction example. Okay. So, for example, let's say we have one, two, three. One, two, three. 1, 2, 3. Okay. Okay. Well, 1, 2. No. 1, 2, 3. 1, 2, 3. Acidic conditions. Okay. So we do have an amine here, we do have an aldehyde here, and we do have a enolizable carbonyl that has 1 alpha hydrogen, right? So the first step that I would do is I would always, form my iminium ion. The second step that I would always do is form my enol. Then the third step for Mannich reaction is react the enol with the iminium ion to get the final product, the beta carbonyl. Beta amino carbonyl, right? Because there's an amino group at the beta carbon, beta amino carbonyl. Yeah, there's an amino group at the beta carbon relative to the carbonyl. Okay, so let's do the first step. We see that this is the carbonyl carbon that's gonna make an iminium with this nitrogen here. So here's a tip: number it from the nitrogen to the carbonyl to see how many membered ring you're gonna form. We're gonna make a 5-membered ring here, and one of the atoms of the 5-membered ring is gonna be this nitrogen atom right here. So I'm gonna number it 1, 2, 3, 4, 5, like that. Right? 5 has the carbonyl. Oh, no. Make a double bond between 1 and 5 because this is the iminium ion that we're forming right here. Right? Because this oxygen is no longer there. We're replacing this oxygen with this nitrogen right here, which is that right there. Okay? And then the N of 1 is going to be attached to CH2, 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 aldehyde, like that. So because N has 4 bonds, it's positively charged. 1, 2, 3. Yeah. Does that make sense so far? I know I'm going a little bit too fast without the mechanism. But I'm trying to show you how to predict the product quickly if it shows up for a predict the product problem. Right? This is not the mechanism, but this is predict the product. Okay?
Okay.
Now, we see that eventually this carbonyl here will become the enol, where this alpha carbon is the nucleophile and this iminium carbon is the electrophile, which when they react together, they're gonna make a 1, 2, 3, 4, 5-membered ring. So when we fuse those together, we're gonna get this. So I like to draw out the 5-membered ring because I know I'm making a 5-membered ring, where this is 4 in green, this is 5, this is 1, this is 2, this is 3. Right? And 1 here, we see that 1 is attached to this aldehyde, like that. Right? And this is the final answer, and we could compare, we could confirm, right? We could confirm by checking if it's a beta amino carbonyl. This is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. So we see that this is a beta carbonyl. No, beta amino carbonyl. I keep saying that. Beta amino carbonyl. That means that there's an amino group on the beta carbon relative to the carbonyl.
Okay.
Okay. So, to finish this off, I'm gonna show you nitrosation, which is the last part of chapter 21, and then I wanna have you try a Mannich reaction, predicted product thing, really quickly. Okay.
Okay.
So, NaNO2, HCl. Okay. So let's say we have a primary amine versus a secondary amine versus a tertiary amine, and we're gonna react this all with the same reagent. NaNO2 HCl. NaNO2 HCl for the primary amine. NaNO2 for the HCl for the secondary amine. NaNO2 HCl for the tertiary amine. The primary amine is going to become a diazonium salt. Right? So it's going to become this, or you might see it as this, N2Cl, right? For Muriel-Jones practice or leavings practice. And this right here, think of this as a very good leaving group. It's like one of the best leaving groups, right? Best leaving group. It's going to leave us N2 gas, nitrogen gas. Okay? And this can do a lot of reactions. It could do SN2, right? Especially if this is a primary substrate. So that's going to do SN2 right there. But let's say that you had a secondary substrate, which is going to be a primary amine still, but it's going to come off of a secondary carbon like this. And we do NaNO2 with HCl. We're going to get this good leaving group right there, which is going to eventually leave, right? Leave as N2 gas and have this carbocation right here. And then from that carbocation, you could do a lot of reactions, like SN1 reactions or E1 reactions, right? From 118A. Okay?
Mm-hmm.
Now, that was the primary amine, which is the hardest one for this nitration. The secondary amine, where the nitrogen has two R groups, is going to be making N-nitrosamine, which is going to be this right here. That N is going to be attached to a N, double bond O, and this is carcinogenic. It can induce cancer, right? So that is just a conceptual thing, like which one of these are carcinogenic, and he might show this versus the tertiary one, where the tertiary one is a N-nitrosamonium salt, which is going to look like this right here. We're basically doing the same thing as the secondary amine. Wait, we're adding an N double bond O, where this N here has a positive charge, and that's the final answer for the tertiary amine. Right? Any questions on that, Rukia?
No.
Okay. Okay, so are you ready for that Mannich reaction?
Yes.
Predicted product? Okay, let's do it. Let me do it down here so I can help you out when you need it, and we could go back to those notes. So let me give you this here. Okay. I put it in different order just to make it a little bit more difficult, but what would you do here?
Okay, so what we did in the beginning was just the double bond O with an H is gonna attack the nitrogen.
So this double bond O would not attack nitrogen. The nitrogen would attack the O.
Yeah.
Right.
Yeah.
But they would form the iminium. But how do you know which one forms the iminium? Like which carbonyl? This one or this one?
Because we know aldehydes were more reactive.
Right. Aldehydes are more reactive. And does this carbonyl here have any alpha carbons at all?
Does it have any alpha carbons?
Oh, I mean alpha hydrogens. I mean alpha hydrogens.
Yeah, it does.
This is an alpha carbon. Does this carbon have any hydrogens?
Oh no, it doesn't. I was
No,
looking at the wrong
yeah.
side.
It doesn't. It doesn't. This one here is also not an alpha hydrogen, right? Because this hydrogen is not coming from an alpha carbon. It's coming directly from the
Mm-hmm.
carbonyl carbon, right?
Mm-hmm.
And because there's no alpha hydrogen here, this is not enolizable. Um,
Okay.
this is why this cannot be an enol. So that's why this has to be the enol right here. Okay?
Okay.
Yeah. So that's why we're choosing this one and this one to create the iminium
Mm-hmm.
ion, which looks like this right here. And this is H2, and then this is boom, boom, positive charge. The hydrogen here goes away. Okay. Now once we
Mm-hmm.
have the iminium, what does this become here?
That one would come and attack like
Yep.
the
The alpha carbon, right? Like you could think of the alpha carbon here attacks this carbon. And when that happens, we are going to create this right here. Where this is the red dot. The invisible hydrogen here is going to be implied. This is the neo bond between the red dot and red star. The red star is attached to a methyl group. And this R group right here, like that, which is this R group right there. And to confirm, let's see if we have a beta amino carbonyl. This is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. And we do see the amino group attached to that beta carbon, and that makes sense.
Okay.
Right? Okay. So one last thing before we end, Rikia. So this is retrosynthesis. If you're given this a synthesis, right, and you want to go backwards to predict what reactants made this beta amino carbonyl, this is what you do. Locate the alpha and beta carbon from the carbonyl, make a cut between the alpha and beta carbon. This whole alpha carbon molecule here is one of the reactants, right? Nothing changes to that, right? This whole ketone there was the reactant. Now, if you look at the beta carbon, that beta carbon was the carbonyl that had a carbonyl before. Make a cut between the beta carbon and nitrogen, right? And add a carbonyl on the beta carbon, which is gonna look like this. And there is an invisible hydrogen here, so I'm gonna add that on to show that that's an aldehyde. And then the nitrogen here was the amine that we had. And to make it neutral, it had a hydrogen before. So that's how we can go backwards to these three ingredients for Mannich reaction, right? Find the alpha beta carbon, cut that. Alpha remains the same. Beta has the carbonyl. Cut the bond between the beta carbon and nitrogen. Get the amine. Like that. Okay. Yeah, so those are all the reactions for chapter 21. Now you could do practice problems like Mira Jones, Levens, and stuff like that. And if you have any questions, you can come ask me. And also, Rikia, I'm changing my office hours from Saturdays and Sundays, like to Saturdays and Sundays, 10 a.m. to 12 p.m. Is that okay with you?
10 a.m. to 12 p.m.
Yeah.
on Saturday and Sunday?
Yeah, on Saturday and Sunday. I can't do weekdays anymore because I have like so many exams coming up. And like I had a nosebleed today in school, and then I realized that I had to cancel all my private tutoring sessions, all my private tutoring packages. So I'm not gonna do private tutoring anymore. I'm just gonna do office hours and focus more on school. So I'm gonna do office hours on the weekends, 10 a.m. to 12 p.m. Not weekdays anymore.
Yeah, that's fine with me. And I'm sorry about your nosebleed.
Yeah, it's okay. It's okay. Yeah, it was interesting. It was a wake up call for sure.
Yeah.
Yeah. Well, good luck, Rukia, and I'll check your midterm one, and we can review that when the time
Okay,
comes.
sounds good. Just the last thing. I'm sorry, you took out your iPad already,
Oh,
but I
right,
was
right.
wondering if you could give me like an extra problem for the Mannich reaction so I can like just do it by myself and then
Yeah.
like try.
Let me do that. I'll give you two actually. I'll give you a predicted product one, and I'll give you a retrosynthesis one.
Okay.
Where you break it open. And the retrosynthesis one is going to be interesting because it's going to be ring. Okay, let's do that. All right. It's intramolecular. Okay.
Okay.
Let me share a screen. Okay. But whenever I do study for my classes in the weekdays, I might like put an event on the school, and maybe we could study together if you're interested.
Yeah,
Yeah.
that'd be great because I do need motivation to study. I just like
Yeah.
get distracted a lot.
Right. And do you do Pomodoro technique? Like, do you do 25-5, 50,
Yeah,
10? Yeah, let's
I
do
do like
that.
50, 10.
Yeah, same. Because like 25 is like once you get in the zone, it's like very hard to get back into focus when
Yeah.
your focus breaks. So yeah, I do 50-10 as well. I'll text you more about it.
Okay, sounds good.
Yeah. Okay. Study motivation. And let's give you. Okay. These three ingredients, they're scrambled because I want you to figure out what reactant would make the iminium ion and what reactant would make the enol, and then combine those two to make the beta aminocarbonyl.
Okay.
And then the product for this one, let me give you. Okay. Yes. Okay, so the first one here, I gave you three reactants with acidic conditions to create the beta aminocarbonyl for Mannich, and then the second reaction here, I gave you the beta aminocarbonyl product for Mannich reaction, and I want you to figure out the three or two, right? It could be three or two. If it's like intermolecular, it could be two reactants that would
Mm-hmm.
create this right here. But it will always have those three ingredients. It will always have an amine, an enolizable carbonyl, and carbonyl that will react with the amine to create the iminium ion, right? It will always have those three components, but it doesn't have to be three separate components. Sometimes they could be together in one reactant if it's intramolecular. That makes a ring.
Okay, sounds
Okay?
good. Thank you.
Yeah, of course, Ricky. See ya, and I'm excited to study with you this quarter.
Yeah, I'm too. Have a
Yeah,
good day
you too, Ricky.
and good luck.
Good luck. Thank you.